talk to you about dark energy, and specifically what its existence means for the history and the fate of the universe. So I think, I don't know, given a number of dark energy talks, and it's always a little bit difficult to know where to begin with this because it's something so big and all-encompassing, I guess. But what I think is a natural starting point is, there we go. In 1929, when Edwin Hubble, who had actually only recently looked out at the spiral nebulae that appeared to be outside of our galaxy and figured out that they were, in fact, entire galaxies outside of our own, started looking at distant galaxies and realized that they were moving away from us at speeds proportional to their distance. So he inferred this from their Doppler shifts. So if you, I guess I can use the pointer here. So when something's moving away, its wavelength is going to be, let's go back. It's going to be stretched out. You can see an example here as it moves. So the wavelength is going to get longer, which means it moves towards the redder part of the spectrum. And the faster it's moving away, the more the wavelength's being stretched out. So the more it moves towards the red part of the spectrum. So what he observed was that distant galaxies were redder. And he never accepted in his lifetime that this is what this meant, but we know now that this was the first evidence that the universe was expanding. Move a little bit here. So this is actually his original data. On the y-axis here, we have the velocity of these receding galaxies, and on the x-axis, we have their distance. And what we see is that this is a linear relationship. We call this Hubble's law, and this figure is called a Hubble diagram. So basically, at some point, we realized that this observation matched a theory that had been proposed by Friedman that the universe was expanding, beginning with a Big Bang. About by the 1950s, that was starting to take hold as an idea. So here is a similar figure. It's not completely the same, but it's conveying a lot of the same ideas, actually. So this is the relative size of the universe over time. Okay, so once in the 50s we know that our universe is expanding. We don't know the geometry of the universe, but I think by about the 80s we were pretty sure it was flat. I'm not going to go into every scenario because I don't think I have enough time, but flat basically means Euclidean geometry, the three angles of a triangle adding up to 180 degrees, etc. So if our universe is flat and contains matter only, we expect that expansion to be slowing. And the reason we expect it to be slowing is that all of that matter is gravitationally attracting all of the other matter and pulling inward, working against that expansion. So this is what we expect to be happening to the scale of the universe over time. Just slowly expanding, but yeah, decelerating. Okay. So then we set out trying to measure that deceleration. And the way that we do that, one of the ways, the main thing we were doing at the time, was with this special type of supernova called a type 1a supernova that detonates with a very uniform and very tremendous luminosity. So I don't know, can you guys see this supernova right here?
Yeah, you got it.
Okay, awesome. So that's a type 1a supernova. This is supernova 2014J, which was found in January of 2014 in the nearby galaxy M82, or the Cigar Galaxy. And so I think you can see, here's the galaxy. It's really just a tremendous amount of light coming from that supernova. It almost looks like one of these foreground stars. So these are very powerful and very, very bright. And yeah, very uniform. And because they're so uniform, we can use them as what we call standard candles. So basically, if you know how bright it's going to be, the further out it is, the dimmer it appears, and actually we can measure cosmological distances very, very accurately that way with a little bit of calibration. So yeah, we were using standard candles, trying to measure the deceleration of the universe. So again, we expect this blue line here, or blue curve, I should say, So in 1998, we're doing this. Here's what we found. So very different. And specifically, two teams found that, one in 1998, one in 1999. So this first one was led by Adam Rees. Here is their Hubble diagram. And they conclude that the distances to the spectroscopic sample of type 1a supernovae measured by their methods are consistent with accelerating expansion, not decelerating. And in the same vein, Perlmutter's team, Saul Perlmutter, finds that the data are strongly inconsistent with lambda equals 0, which would be matter only, with the lambda equals 0 flat universe model that has been favored. And if our inflationary theories are correct and the universe is spatially flat, then the supernova data means there must be a significant positive cosmological constant. Okay, so this is 1998, right? How much do you think we've figured out since then? Yeah, almost nothing. So 2 decades, yeah, it's not great, guys. 2 decades of searching. Here's what we know. We know that the universe is about 68% dark energy, about 27% dark matter, and about 5% ordinary matter. It's actually very hard for me to see the screen up here. Then also we know of that ordinary matter, so only about 0.5% of the universe is visible matter. As in, like, ordinary matter would be matter made of the same stuff that you and I are, but a black hole is made of the same basic stuff but isn't emitting light, so that would be like part of this other 4.5%. But yeah, so only 0.5% of our universe is visible matter, which is astounding, especially that we've been able to figure out about the other 99.5% with just that 0.5%. But anyway, so we know that most of the universe is dark energy. But beyond that, dark energy is just a placeholder name for something we don't understand. All we know is it's causing this repulsive force that seems to be pulling the universe apart. And yeah, okay. I always feel at this point that I need to give a little clarification about the difference between dark energy and dark matter, because if you work on one of those and people keep confusing it with the other one, it gets really annoying, because they're almost opposite things. So dark matter, it's matter, it's gravitationally attracting, it's interacting with other matter. It's dark because it's not emitting light, even though it's matter. And we pretty much understand how it behaves. I mean, it works mostly on galactic scales. We know that galaxies are in galactic halos. We can even kind of map out the distribution of dark matter. Dark energy, on the other hand, is exerting a repulsive force. It's actually sort of opposing gravity, so I don't know, like I would tell my students it's anti-gravity. Dark mostly is just a cool way to say we're pretty lost. You could also say it's like the fact that it's weakly interacting. The only real thing that these have in common is that we don't know what they are and we sound cool talking about them. Yeah. So now that we've got that out of the way, on to what we think. We've talked about what we know. So we think that dark energy is in the form of a cosmological constant, which would be the same as vacuum energy. So in this case, dark energy is coming from space itself. It's this vacuum that's not a true vacuum. We have sort of virtual particles out in the vacuum of space, particles and antiparticles that are appearing and they're annihilating one another, and they carry energy with them the same way normal particles carry mass, and that energy is exerting a repulsive force, and yeah, so really there's like a negative pressure in that vacuum. The cosmological constant is constant in time. This plot is a really simple solution because it's constant in time. It's one value, makes all the math pretty straightforward, relatively speaking. And yeah, we like to denote it lambda. I don't know if people can see that. So we call the prevailing cosmological theory lambda CDM for cosmological constant dark energy and what we call cold dark matter. Okay. So the best part of this model, in my opinion, is the history of it. So in fact, Einstein invented the cosmological constant. which may be very confusing to you. No, he was not a time traveler. So when he was penning his theory of general relativity, the math indicated to him that the universe needed to either be expanding or contracting. And he was like, that cannot possibly be right. I'm going to put in this fudge factor right here, lambda, that keeps the universe static. And so he does that, and then a few decades later, we realize that the universe is expanding, and Einstein is like, oh my god, that was my greatest blunder ever. And sadly, he went to his deathbed thinking he had dismissed one of the most important discoveries of our century. Although, I mean, overachiever, he did plenty. But, but anyway, then in 1998, when we observe cosmic acceleration, we realized that if you just give lambda a positive value, that does the trick. So, thank you, Einstein. Now, there's always the possibility that the cosmological constant is not the answer here. It agrees with most of our observations within about 10%, but there's obviously that margin of error. And then also there are some discrepancies. Furthermore, so there's something called the cosmological constant problem, which is basically that quantum field theory predicts that the vacuum of space should be stronger than it is. The vacuum energy should be stronger than it is by quite a bit. And we don't see that. It's also peculiar that it's on the order of the mass density of the universe, like the density of dark energy is, by which I mean that the density of dark energy is close enough to the density of matter that matter is able to win out locally and have structure form. That's a pretty remarkable thing. Yeah, and then also it's kind of philosophically weird, right? Because the cosmological constant can only take one value. So one person who's come up with some solutions to this is actually UT's own Nobel laureate, Steven Weinberg. And he has proposed that we could solve this problem with a multiverse, so many, many big bangs, many cosmological constants in different universes. And each universe would have the cosmological constant taking a different value, and then it would be sort of self-selecting, right? The idea is that we're here to observe because we live in a universe that has a cosmological constant that is, or a vacuum energy density that's on the order of the mass density, and thus structure can form and life can arise. So, I don't know, interesting to think about. Also, there are a ton of other theories out there. I believe Perlmutter said in his, so the guys who discovered this won a Nobel Prize. So Perlmutter said in his Nobel speech that in the days following the discovery, the months following the discovery of cosmic acceleration, there were tens of papers published every day with new dark energy theories. So you can just think about how many theories that must have been. So, I don't know. It could be any number of things. My research area is mostly sort of alternative ideas. So most of these would fall into the category of quintessence, which is just dynamic dark energy. So this is dark energy, instead of being inherent to space, is actually a field called quintessence, like my name, that fills all of the universe. This is a lot like a gravitational field or an electromagnetic field, except that those are localized and this is pervading all of space. And so this model is dynamic. I hope you guys can see that over there. So the strength can either grow stronger or grow weaker with time, and its effects on the universe will change with that. Also, just because there's so many different theories and we have other ways to differentiate them, the evolution can slow down or speed up with time. So you could have freezing dark energy, which is evolution slowing down, thawing dark energy, which is evolution slowing up. So this would be getting stronger, getting weaker. Both of these are thawing. It's also possible that there is no such thing as dark energy. So we call this modified Newtonian dynamics. In this scenario, there's no dark energy, and instead we do not understand gravity well. And it is Newtonian on small scales and really different in some way, who knows, on larger scales. So I don't know, intriguing idea. It doesn't really explain anything yet. There's so many Mons theories out there. Yeah, they have a big problem explaining the current data. So right now, most people believe there is dark energy. Okay, so now that we've gone into the possibilities, we can talk a little bit about how the prevailing theory fits into the history of the universe. So here is, oh boy, that is like really close to the bottom. So here is the history of the universe beginning with the Big Bang and going all the way to today. And here is a plot showing how its different density components have evolved. So we begin with the Big Bang. This is actually offset a little bit. It should begin after inflation, but that's me being nitpicky. Big Bang, this period of rapid inflation, and then suddenly we have a lot of scattering happening, and in the early universe, the radiation density dominates. So exotic particles are scattering, the radiation density dominates, and slowly, as they're scattering off of each other and the universe is expanding and it's cooling, protons and neutrons are able to form, and more time passes and it's still expanding and cooling, and now atomic nuclei begin forming, and then, let's see, before we get to actual atoms, but once we already have nuclei, the matter density begins to overtake the radiation density. So we've been in an era that was radiation dominated. And whatever density component's dominating, that's controlling the dynamics of the universe. So suddenly we make this switch to a matter-dominated area, and then things continue. We have the CMB right here, so that's right where the surface of last scattering is, and suddenly the universe becomes transparent to radiation. So now we have the dark ages, and then the first stars and galaxies form, and somewhere between then and now, the density of dark energy actually overtakes the matter density, and that's happening because the amount of matter is staying the same, but the universe is getting larger and larger and larger. But dark energy is constant in this scenario. So anyway, we entered this dark energy dominated area, or era that is causing that acceleration. This was a lot to take in. The next figure might help a little bit. So the fate of the universe with dark energy in the form of a cosmological constant would be, we have this constant strength of dark energy. So we expect the universe to accelerate, and it's just going to keep accelerating as it expands, and eventually everything's just going to freeze. As it gets bigger and bigger, it's cooling, and eventually we reach absolute zero. Stars are extinguished, all that. So we call this the Big Chill. So the last slide, which might have been a little bit confusing, we can see the matter domination to dark energy domination happening along this curve. So the relative scale of the universe is going to be increasing this whole time, no matter what. But we can actually see a part where the relative size is increasing, but we're looking at deceleration. The slope isn't picking up super dramatically. And then we move over to dark energy dominated, and this really takes off. If dark energy is in the form of quintessence, what we see instead is two scenarios. So if the strength is increasing, we're going to have that same sort of cosmic acceleration, but on an even greater scale. It's just like a really runaway acceleration. And the universe is actually eventually going to rip apart, which is crazy and cool. Also, if you've ever seen Annie Hall, there's a great scene about that in it, where Alfie's at his psychiatrist. Well, by the way, wasn't this like the 60s? It's weird. But anyway, he's like, the universe is going to rip apart. We're all going to die. And they're like, we're in Brooklyn. Calm down. That would be the big rip. If the strength of dark energy is decreasing, instead we see the size of the universe continuing to grow, but instead of accelerating, it's eventually going to start decelerating here, and then it actually will come to a stop at some point and turn over, and then the size is going to decrease. It's going to collapse. And so we call that the big crunch. So we've got the big rip and the big crunch. Or, in our modified gravity scenario, we have no idea. At some point in this talk, I decided that Mond was Keanu Reeves, and I really liked it, so that's what happened. So Mond makes no specific predictions. It depends how gravity acts on certain scales, so fate unknown. Okay, so we have just given you guys like a lot to think about. The truth is, so we think we're headed for a big chill, but we don't know for sure. It's probably going to be a long time before we know with like really good confidence. So you're probably thinking, what's next? I want to know. So we have these many dark energy experiments that are starting up right now. I am extremely biased towards our local dark energy experiment, AoTATX, out at the Hobby Everly Telescope at McDonald, which is starting up very soon. So hopefully we will learn something good from those. And yeah, that's it. Thank you. Feel free to tweet questions at me, and also please visit hetex.org and read about hetex.
Questions for MC Quintessence? All right, right up front here. Yeah.
Opposite, yeah. Yes, yeah, that ratio is changing. So that would be that density changing. So the matter density is decreasing and the radiation density was decreasing. So yes.
Questions? Straight back in the glasses there.
Yeah, I'm wondering if you could say real quick why the majority of people seem to be drawn towards theory of dark energy instead of the Mond theories, especially if not much progress.
Please repeat the question.
Yeah, I forgot. Okay, so the question is, why are we drawn towards the theory of dark energy and not Mond? There are a lot of like observational reasons that are kind of complicated for this setting, I feel like. I mean, the cosmological constant fits data well. It does a better job of explaining observations than any Mond scenario. And frankly, it's easier to think that Newtonian dynamics holds than to think, like we know we have Newtonian dynamics, we know that relativity also factors in, but we don't want more amendments to Newtonian dynamics. That's pretty scary. And yeah, if dark energy fits, I don't know. But I will say that my own research area is kind of suggesting that we have maybe been a little too quick to embrace the cosmological constant, and there could be some time evolution. So I don't know.
Is anybody upstairs? Right up here.
So could you talk about that? You didn't mention baryonic acoustic oscillations.
Yes. Yeah, so I didn't get into the ways that we observe dark energy because we've had some talks about that before. Oh, I'm so sorry. So he's asking how baryonic acoustic oscillations fit into this picture, how we use them to detect dark energy. So baryonic acoustic oscillations basically are, when the Big Bang happens, we have these quantum fluctuations in the very early universe. And then by the time we get to the cosmic microwave background, the surface of last scattering, those fluctuations are frozen in like sound waves at a characteristic scale. And we can measure the expansion of the universe. Actually, I have, where is it? Sorry, it's taking, where is it? Sorry guys, right here, okay. So this would be like a baryonic acoustic oscillation type thing. So this is using galaxy pairs to measure the expansion of the universe. So baryonic acoustic oscillations give us a standard ruler, the same way we have standard candles, that allow us to measure how this characteristic scale that was set back at the time of the CMB, which is like redshift 1100, how that scale has changed over time. And we just measure it in the preferential clustering of matter around us, of galaxy pairs. So.
One more question for MC Quintessence. Second row here in the sculpture.
Hey, you said there's a lot of theories. Sounds like a lot of money invested in heavy stuff. Who are the people that approve the grants? What kind of expertise do they have?
Oh. Yeah, so he's asking who's approving these grants and commenting that this is heavy stuff. I am a lowly grad student, so I'm not dealing with that. They just pay me and I do my work. I don't know, the National Science Foundation funds a lot of stuff. I don't even know. Jeff, who's funding stuff that you work on?
ATX is funded by NSF, NASA, the state of Texas, the university, and various generous donors. But most of them are peer-reviewed, so other scientists actually approve this and not. And it's very hard to get money, so that's why I'm leading this team. One more quick question for MC Quintessence. I'm not going to end on that downer. Front row.
Yeah, that's a super confusing point. So there are, oops, wait, no, I went past it, didn't I? So there are, you can sort of think about it as there are two types of dark matter. So in fact, this dark matter is not made of baryons, the stuff that we're made of. So this is baryonic matter. This is something else that we have not been able to detect yet. But we think it's something called weakly interacting massive particles. So it's just of a different nature. Like, if it is WIMPs, as we like to call them, because we're astronomers and we love acronyms, then in fact, dark matter particles would just pass right through you. They don't interact the way we do, they just gravitate. So this is dark matter, and 4.5% is also dark matter, but they're very different dark matters. So, yeah.
Let's thank MC Quintessence one more time.